Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Good afternoon. Good afternoon.
Good afternoon, sir.
Good afternoon. You can give your attendance in the chat box. Okay. Just mention your roll number. That will be enough. Those who are joining new, you can mention your roll number in the chat box. Fourteen students have joined. We'll wait for 1 or 2 minutes more. Then we'll start. Okay. So let us start because 15 of you have joined. Let me share my screen first. The slide is visible. Please confirm me.
Yes, sir.
Okay. So this was, and my voice is audible, right? Hello, my voice is audible.
Yes,
Yes.
sir. Yes, yes.
Okay. Uh, okay. So this was our last class discussion, actual regenerative cycle. Today, someone is joining. Please wait. Okay. So today, basically, we will discuss. We'll try to discuss one or two problems on it, both the reheat cycle and the regenerative cycle, both. Okay, so that your concepts will be clear, because understanding is fine, but you have to solve problems. No one will ask you about the theory, but theory you have to know to solve the problems. That is correct. Now my question is there any doubt regarding this last this phenomenon, actual regenerative cycle or reheat cycle, whatever? Is there any doubt? You can ask me first, then we can start. If there is any doubt, feel free to ask regarding the last class or last to last class. Okay, so if there is no doubt as of now, I asked you to see two things in the last class, that is the steam table and the Mollier chart or Mollier diagram. Have you seen those two things, so that it will be helpful for me to discuss the problems? Have you seen the Mollier chart?
Yes, sir.
Okay. One student has replied only. So what I will consider, others have not seen. Hmm?
There is in place.
Okay. So now, so I will discuss to the problems. Prior to that, let me uh, go for it now. So I will show you. So my slides is properly visible, right? My slide is
Yes,
properly
sir.
okay. So prior to going the discussing the problems, let us discuss two more new things in the sense two more topics, that properties of an ideal working fluid in a vapor power cycle. In a steam power plant, the ideal working fluid we use as water, that all of it know. But what should be the ideal properties? Because ideal, yes, it may not be achievable practically, but there are some properties which a fluid should have, your when it is thinking of as the ideal fluid, right? So what are those properties that a fluid should have? The first one, you see, the fluid should have high critical temperature and pressure. So whatever the fluid I'm using, if it is water or whatever any type of fluid if I'm using, the fluid should have high critical temperature and pressure. Now that critical temperature and pressure means the topmost point or the top notch point of the vapor dome, right? You know what is vapor dome. The top notch point is the critical point. So that critical point, that means the corresponding temperature and pressure should be high enough, okay, so that the boiler pressure and the condenser pressure can be controlled. Next is the saturation pressure at the temperature of heat rejection. The saturation pressure at the temperature of heat rejection should be above atmospheric pressure. Try to understand. Saturation pressure at the temperature of heat rejection, that means heat rejection temperature is the T2, or which on which part it happens? It happens at the condenser, right? Because in the condenser we reject the heat. So saturation pressure, because and also as it is a phase change, as in the condenser we are having the phase change, what is happening there? Only the latent heat of from the steam is given out, and that means that is the heat rejection. The latent heat rejection is basically happening over there. So that should be that pressure, whatever the condenser pressure we are talking about, that condenser pressure should be above atmospheric pressure. But I should mention over here that practically it is not, there is very few fluids that is practically used where we can get the saturation pressure at the heat rejection which is above atmospheric pressure. So for that, what we have to do is that we have to create a vacuum. Basically we have to create a high vacuum inside the condenser, so that that pressure we have to maintain. Basically for that we have to give some external work. Okay, so that means there are some losses. Always remember, condenser loss is the biggest loss in in any thermal power plant. Okay, so that is ideal. That means this point, whatever the line it is written in front of your screen, that is the ideal, but that is not achievable all the times. So saturation pressure at the temperature of the heat rejection, that means at the condenser, that should be above atmospheric pressure. If it is so, we don't need to maintain that vacuum. Okay, that is the point. But practically we have to maintain the vacuum as we are not having that type of fluid. Next is the specific heat. Specific heat of the liquid should be small, so that little heat transfer will be required to reach boiling point. Okay, so I'm discussing one by one points. Otherwise it will be very difficult for me to understand where you are having the doubt. Is it clear? First two points are clear.
Yes, sir.
Okay, so
Yes, sir.
third one should be also clear. If you know only what do you mean by specific heat, if you know that, third point should be also clear. Specific heat of the liquid should be small. That means what? Specific heat means the property by which it can retain the heat. Any material which can retain the heat. So specific heat of the liquid should be small, so that little heat transfer will be required to reach the boiling point. Consider the case of boiler. We are heating the water. To make the steam. So if the specific heat of the liquid, that means specific heat of the working fluid, is high, then what will happen? It will not take and it will not reject heat much. That means whatever heat it is having, that particular fluid will try to retain that heat. That means very less tendency of the heat transfer will be there. Heat capacity and heat transfer is different thing. We need what? We need high heat transfer capacity. So for that we should have a working fluid which is having low specific heat, okay, to reach easily the boiling point, to generate the steam or to generate the vapor. Next one is the saturated vapor line in the TS plot should be very steep to control the quality of the steam at the turbine outlet. That means you just recapitulate the vapor dome. On the left side, we are having a line that is known as your saturated liquid line. On the right side, the line is known as your saturated vapor line. Now, in the TS plot, the expansion line means the if I can remember the naming may be obviously different. 1 to 2 process, the turbine expansion process. If it is ideal, or it may not be ideal. If it is ideal, it will be a vertical line. If it is not ideal, it will be a slant, a bit tilted towards right side. It will be that we have discussed in the last classes. So that line, that expansion line should be very close to the saturated vapor line of the vapor dome. Okay, so is these two things are clear? Otherwise this point will be not understood. Saturated vapor line, that is the part of the vapor dome, and the expansion line from the turbine 1 to 2, that means the vertical line. If we consider the ideal case, the isentropic process, then it will be a vertical line. So what is the importance of vertical line? The exhaust, you see, the saturated vapor line in the TS plot should be very steep. That means the saturated vapor line of the vapor dome should be very steep. Okay, the slope should be such a fashion that it should be very steep to control the quality of the steam at the turbine outlet. That means if it is very steep, what will happen? If it is very steep, I should ask this question to you. If this saturated vapor line of the vapor dome is very steep, what should be, how it will affect the quality of the steam at the turbine outlet? Any idea? Answer me. If it is very steep, the saturated
Sir,
vapor
the
line.
dryness fraction will be less.
Yes, dryness fraction will be what?
Sir, less.
Dryness
So,
fraction will be less or high?
No, sir, it will be high when
high, sir, high.
It will be
High,
high. Dryness fraction
high.
less means
Yes.
it contains more
More amount of
more amount of water,
liquid.
right?
Yes,
But
yes.
if it is very steep, right side the vapor line, and the expansion line is as it is, say, so what will happen? The quality of the steam at the turbine outlet is high. Quality of the steam means that the dryness fraction of the steam, it will be more dry, isn't it? This point is clear to all of you?
Yes, sir, yes.
yes, sir,
Yes.
yes, sir.
Okay. So next is the freezing point. The freezing point of the liquid should be below the room temperature so that it does not solidify in the pipelines. This point may not be relevant to our countries because we are the tropical countries here, like India, Bangladesh, Pakistan, and like this type of countries, Asian countries. But where but if we take any countries like any your European countries, there this point is very important, the freezing point, because there is all the year, most of the months of the year, they are having very cold weather. So if the freezing point of the liquid is not below the room temperature, what will happen while the steam or while the that fluid is flowing either in the liquid phase or in the gaseous phase? If when it is flows through the pipeline, then what will happen? It will automatically solidify, right? If the freezing point is not that much. So the freezing point of the liquid should be below the room temperature. Room temperature means, here it is mentioned room temperature, the standard atmospheric temperature, you can also say. So it should be designed in such a fashion it is not solidify. When it is not when it will not solidify, when the freezing point is much below, isn't it? So this point is important for the cold weather countries. It may not be much applicable for India, but this point you should remember. Next is the fluid should be chemically stable so that it will not react with the materials of the construction, because that is very obvious. Someone is entering now after 15 minutes of the class. Okay. So okay, this point we are discussing, the fluid should be chemically stable. That means it should not react with any parts of the pipelines or valves or whatever the parts, the metallic parts we are having of the construction. It should not react with that. Okay, that's it. That is the chemical stability is required. And the last one is the fluid should be non-toxic, non-corrosive, less viscous, and low in cost. Obviously, the cost is the important parameter. You may attain this the above properties for a particular fluid, but if it is highly that means if the cost is very high, or it is very costly, then the production cost of the electricity will be very high. You cannot sell that, right?
So
So that
usually we use water only, no?
generally we use obviously
Yes.
water, right? But actually water is not having all these properties, but water is nearly, water is abundant from the point of view of the availability, and it maintains some of the properties. Obviously it is not practically possible to get for a particular working fluid all these properties. That is not practically possible for by using a single fluid. By using a single fluid, practically it is not possible to attain all these points, but these are some ideal points. Okay, but water, why you use water? Water is maintaining most of the that means most of these properties. So, and it is obviously it is free. We have to only treat our water a bit and we can directly use. We need not to buy the water most of the cases, and so that's why the water is the most commonly used in the thermal power plant. And the last point, whatever I was discussing, it should be non-toxic, non-corrosive, and less viscous. But still, there will be some corrosion will be there in the pipelines after a certain period of time. Some toxicity may be there by reacting with some chemical additives if we add in the boiler drum, but that is negligible. Obviously, each and every parts of the power plant is having some depreciation. So after a certain period of time, it may degrade, but ideally say for a 5 years or 10 years period of time, that should run your that means your efficiently, I should say. And less viscous means it should not be highly viscous. Water, the viscosity is very less. So if we have some highly viscous fluid, that means then the pumping power will be more. That means the pump loss will then be high. And obviously if the pump loss is high, then the network your output will be less. That will affect the thermal efficiency. So these are few points that you should keep in your mind. I have just mentioned the points in the slide, and you can elaborate by your own words. But if some questions may come for your say your 5 marks or 7 marks, you have to discuss it. You can write this point and you can elaborate according to you. Okay, but is this clear? Is there any doubt in the slide? Hello?
Clear হয়েছে স্যার, clear.
Okay, fine. But as I told that no single fluid can maintain all these properties, or no single fluid is available to us to maintain all these properties. There is a need of binary vapor power cycle. Have you heard this term earlier? Binary vapor power cycle. How many of you heard?
Thermodynamics এ ছিল
Yes, sir. Yes, sir.
ছিল তো ঠিক আছে, কতটা মনে আছে সেটা বলো।
মনে নেই।
হ্যাঁ, আচ্ছা, যার মনে আছে বল। দীপ্তদীপ, সোমনাথ।
স্যার এটা কম্বাইন ভেপর পাওয়ার সাইকেল তো?
হ্যাঁ, combined. Binary means there will be two. Binary means it itself, it means two, right? But what is the need of this? Why we have to think about this? Okay, each and everything is having some significance, right? Unnecessarily we don't
Sir,
do anything.
there are
Yes.
two different fluids used for different purposes in this
Yes.
binary vapor cycle.
Yes.
And
What
sir,
are
I
those
don't
two
remember
fluids?
that much, but sir,
Example. I need
sir, in
example.
one water
Those
is
two
used.
fluids may be
Hello.
anything, but I need an example.
Yes, sir. I don't remember that, sir. But,
Okay.
sir, for two different conditions,
yes.
we use two different liquids
Yes, that is correct. Two different
uh,
liquids. Why we
to get
use two
proper
different
or
liquids?
more
Why we
efficient
use?
machines.
Why use two different liquids? What is the need of use? Unnecessarily, I will not use, right?
Yes, sir.
Right. So the reason is the last slide. If you have understood the last slide, and repeatedly I told 2 times, 3 times that no single fluid can achieve basically all these properties. So if we try to achieve more and more the properties, then the need of this binary vapor cycle comes. That means if we use two separate, that means two separate Rankine cycle, that means two separate vapor power cycle, and if we add those two cycles in series, then that will create a binary vapor cycle, and that will give obviously higher output, and that will maintain most of the properties, not all, again I'll say, but most of the properties, the last slide that we have discussed, right? So generally you see no single fluid can meet all the desired properties for being an ideal fluid in a cycle, as I was talking about. Though water is better in overall condition, but there are few fluids like diphenyl ether, aluminum bromide, mercury, etc. There are so many fluids which are much better at high temperature range. That means these fluids, diphenyl ether, aluminum bromide, mercury, right? These fluids, that means these fluids shows some better performance at high temperature range. Why? Because their critical temperature and pressure is very high. That means I should say their critical point is very high compared to the water. So that was a criteria, that was, that was a criteria for being an your ideal fluid. But if we use water, I may not get that. Okay, but you see, these fluids, whatever these fluids I have mentioned, diphenyl ether, aluminum bromide and mercury, their performance in the low temperature and low pressure range, that is very low again. That means these fluids, these three fluids, for example, I have mentioned, these three fluids are suitable for high temperature range only. They are not suitable for low temperature or low pressure range. So what should I do? So I can do one thing. For high temperature range, if we use uh, just your any of these, okay, and for low temperature range, what I know, water is very suitable, water is easily available also, and water is suitable also. So if we can club these two, or if we can add these two types of fluid in series, I can get something better than the single water or single mercury cycle or not. Answer me this one first. Do you agree with me or not?
Yes, sir. Yes, sir.
That means separately, if we use water, whatever the efficiency I will get, or separately, say mercury cycle, if we use separately, whatever the efficiency I will get, but those two efficiency will be less compared to what if we add these two in series. That means two different cycles will be there. Obviously, water, that means steam vapor cycle will be there, and say mercury vapor cycle will be there. If we can add these two in series, whatever the cycle we will get, whatever the binary vapor cycle I should say that I will get, that efficiency will be obviously higher, right? So you see here, I told two times for use of your use of mercury, right? But these two, the diphenyl ether and aluminum bromide, these two materials are also suitable for high temperature range. But why we are not using this diphenyl ether, the first one, diphenyl ether and aluminum bromide? Diphenyl ether is basically a for being a organic compound. What happens at a very high temperature, it there is a tendency for decomposition of any organic material, we know it breaks the chains, so there is a chance for that. So that's why we are not using that. And aluminum bromide, this may be used, obviously this is not a organic material, but still the availability of mercury is much more higher than the aluminum bromide. So for that reason we will use the mercury. That is the reason. If anyone asks that except mercury there are so many fluids, those are suitable for high temperature, that means suitable in the sense whose critical temperature is higher, okay, at high level. So but why we go for in most of the cases for the mercury, that is the reason. You can give these two examples, that if we use like diphenyl ether, any type of your organic compounds, there is a tendency for breaking their chains, the compounds, and creating some sub compounds at high temperature. And obviously the second reason is the availability. Mercury, the availability is high compared to the other materials. Okay, so
Sir,
among these,
cost of
yes,
mercury is less than aluminum bromide.
cost is actually cost of the mercury. Actually, aluminum bromide is that means you have to formulate much, but mercury you can get easily. Okay, that is the one reason. Cost exactly I cannot say right now, but yes, mercury is cheap compared to the aluminum bromide, I think. Okay, still I have to check. I cannot assure you
Okay,
right
sir.
this point, but from the
Okay, sir.
availability point of view, I can say, right?
Yes.
So mercury is available more compared to the others. So among these, mercury is used practically. That is the reason. Yes. So you see, for this reason, mercury vapor leaving the mercury turbine. Okay, you may not you may not be understanding this one first, but still you read this second point. Then I'm showing you.
আর মার্কারির
that
তো ভিসকোসিটি অনেক হাই।
Yes, it is high. I understand that, but it is not. I am not using for the whole. I'm using two different. Mercury cycle will be separate, and the steam cycle will be also there. Both the cycles will be there. Okay, not only the
Okay,
mercury
but
cycle will be
at
there.
sir very high temperature, the mercury's viscosity will decrease.
Yes,
As
that is
we,
also
sir,
correct.
yes.
That is also correct. The effect of temperature on the viscosity will also work. It will be not that much of high. It will be high, obviously. If you compare with the water, yes, that will be high. But not that much of high. When we use high temperature, then obviously the viscosity will decrease, right? Yes, pumping power will be, if you compare the pumping power with the water, obviously the pumping power will be higher in the case of mercury. But if you calculate the total work done, that will be obviously higher, much more higher. Okay, so I will come to that TS plot, then it will be more clear. So for this reason, mercury vapor leaving the mercury turbine condensed at high temperature, and its latent heat of rejection is utilized in evaporating water to the steam to run the conventional turbine. That means conventional steam turbine will be there, and also mercury that means mercury vapor turbine will be also there. Two separate cycles will be there. Okay, so whenever we are adding these two, whenever we are adding these two cycles in series, we are calling that type of vapor power cycle as binary vapor power cycle. So thus binary vapor cycle is nothing but the two different vapor power cycle working in two different fluids. Obviously that should be the condition. Two different working fluids should be working in two different cycles, are coupled in series, and heat rejected by topping cycle is fed to the bottoming cycle. Topping cycle and bottoming cycle is very important term. Top cycle, different books use different terms. Top cycle or bottom cycle is also used, few books, right? Topping cycle means the cycle, the vapor power cycle which operates at high temperature, and bottoming cycle means here obviously the water or the steam cycle. Okay, that is working in the low temperature range. So this is the basic introduction of the binary vapor cycle. Now we will come to the analysis. But addition of mercury cycle with steam cycle will increase the mean temperature of heat addition. Yes, that is the reason. That is the reason why we are doing this, to increase the efficiency. But how will increase the efficiency? That will come obviously from the higher mean temperature of heat addition, because heat addition is happening in two cycles, right? So obviously the mean temperature of heat addition will be higher. So let us see the analysis part. Yes, you see this one. So you see two different vapor power cycle is there. The TS plot only I am showing you. The similar will be the HS plot and all. The upper cycle, this cycle you see the mercury cycle. This is known as your topping cycle, and this steam cycle is known as your bottoming cycle. So the naming is again up to you, A, B, C, D, and this is A, B, C, D is the mercury cycle. Now you see B to C. What is the B to C part? B to C part is what? B to C part is the condenser part, mercury condenser. So B to C part is the mercury condenser, and that here what is happening in B to C part? B to C part, the heat is rejected, right? So that heat is fed to this 5 to 6. That heat is fed to this 5 to 6 part. So that now see, this 6 to 1 is not the boiler part, this is the superheater part, and this 4 to 5 you can say the this part is let us assume this part is heated by some regeneration and all. This heat, or you can say the boiler also, this part is boiler. If you take this part is boiler, because superheater or whatever those names I'm talking about, this is nothing but the boilery accessories. These all are the boiler accessories. So this 6 to 1 and 4 to 5, these parts are external heat addition. I repeat, 4 to 5 and 6 to 1, these two parts in the steam cycle I'm talking about, that is your external heat addition by the boiler or the superheater, whatever. And this 5 to 6, that means, sorry, this phase change 5 to 6, this phase change part of the water to the steam, that heat it is taking from B to C, that heat rejection. Here it should be written, that means here the Q whatever it is rejected, that is fed for this 5 to 6 part. Is that clear, this point? Then I'm coming to the enthalpy analysis.
Yes, sir.
Yes, sir.
So
It's clear.
whenever we will do for the enthalpy analysis, that will be again, it will be more clear. You see the key one, what is the total? Now see, don't think that these two are the separate cycle. You have to think about that this total is a single binary vapor cycle. Okay, single binary vapor cycle. Problems also may come from this part also. So whenever I'm talking about this binary vapor cycle, total heat added I have to calculate. How I can calculate total heat added? First you see, take the binary vapor cycle. Now m is the mass, that is that value of m I don't know here, that we can find out easily. So this m kg of mercury is running over here, and 1 kg of steam is running over here. Okay, and it has been seen that to evaporate 1 kg of, that means your steam over here, 1 kg of water, that means from 5 to 6, 7 to 8 kg of mercury is required. Okay, in this ratio we add. Okay, in this ratio there is some practical calculation. In this ratio we have to add the mercury. So that m is the amount of mercury in kg that is running, and what is the part in this mercury heating? A to D, you can see, from starting from this D to the A, that is the heating part. So HA minus HD, HA minus HD is your HA minus HD is your mercury cycle heat addition, plus what is happening, H1 minus H6. You see, H1 minus H6, this part. Okay, plus H5 minus H4, H5 minus H4, as I was talking about, H5 minus H4, this part, right? So these are the external heat addition. By mistake, do not write H6 minus H5, because H6 minus H5 is nothing but HB minus of HC. Okay, not HB minus HC, M into HB minus HC, that I will come. So this Q1 is this much. That is the heat added, total heat added to this binary vapor power cycle. What will be the Q2? H2 minus H3. Q2 will be, don't take Q2 by mistake, this B to C part, because this heat is not rejecting. This heat is utilized again in the steam cycle. So HB minus HC multiplied by M or whatever it is, that heat is not heat rejected from the binary vapor cycle. It is again utilized in the steam cycle. That is nothing but H6 minus H5. So what is the Q2 in this binary vapor cycle? Only this one from the steam cycle, H2 minus of H3. Okay, this will be the heat rejected. So WT now, obviously it will be added. M into M is for mercury, M into HA minus HB, very easy, plus H1 minus H2 is for the steam cycle. We have to just add it. Okay, that is the total turbine work, WT. WP will be similarly the same thing, right? D minus HC, it is not HC minus HD, HD minus HC multiplied by M, because M amount of mercury is running, and plus for the steam cycle H4 minus of H3, this part, that will give me the total pump work. So if we use this one, eta cycle, this is very simple, that WT minus WP by Q1, whatever the values you will get, that you will just put it and you will get the value of eta. And how to calculate the mass, energy balance of the mercury condenser and the steam boiler? This energy balance will give you the value of M, or the value of mass that is running in the turbine cycle, in the mercury cycle for 1 kg of steam cycle. Okay, how we can write this? What will be the equation? Who can tell me? What will be this energy balance? Mercury condenser and steam boiler. What will be the energy balance? Hello? Who can tell me? Hello?
Sir,
Yes,
M,
sir.
Yes.
M into HB minus HC equal to H6 minus H5 এরম কিছু হবে?
Very good. But be confident whatever you are saying. Just you are saying right. Okay, it is very easy. Just energy balance. So how much enthalpy is entering, how much enthalpy is rejecting. Okay, you have to, but don't forget to put this M. If you forget to put this M in the equation, then it will be wrong, and obviously will not get the value of M. My target is to calculate the value of M from this equation, and that M will be used in all these equations where you are calculating Q1, Q2, not in Q2, in WT, WP, each and every equation M is there. So this value of M will be required over there. Is that clear, this analysis? It's very simple. Just
Yes, sir.
only you have to remember the heat rejected in the mercury condenser is added for the phase change of the water from water to steam. Okay, now it may so happen that in the problem it is mentioned which part is utilized. This heat rejected by the condenser of the mercury cycle is utilized on which part. If it is written that for the whole heating, if it is required, that is not the case. But you say except superheating, if it is mentioned, that means from H4 to H6, that will be by this your HB minus HC. Now that will depend, you have to read the problem properly. What condition is given? Condition in the sense, if nothing is given, now no condition is given, then this is the ideal case, whatever I have shown, that only this HB minus HC multiplied by M, that much of it is utilized to for the phase change only. That is the ideal case. Okay, so Uh, please wait. So you see, this coupled cycle, I'll show the coupled cycle in the next class. But prior to that, whatever so many things we have discussed, but we have to discuss some problems also, isn't it? Have you seen any problems from the reheat or regenerative?
No, sir.
Okay, so let us. Yes,
Sir. So can you just share these lectures over some Google Classroom or links? It will be
this
helpful.
PPT.
No. The entire meeting.
Okay,
The
meeting,
lecture.
meeting. Okay, meeting. I can share easily. Okay, I will because automatically it is saved in the drive link. I will share the link.
Yes.
Okay,
Thank
I'll
you,
share
sir.
the link.
Thank you.
Okay, I'll share the link. Sure, not a problem. Okay, so now before going to this your problems, let me show you something in the sense one time at least Mollier diagram. Can you see this image? Please confirm me the Mollier
Yes, sir.
diagram.
Yes, sir.
Okay.
Yes, sir.
Uh,
Yes.
okay. So how to? Okay. Let me zoom it up a bit. Okay, so you see this is I'm having one snap of this your Mollier diagram. You will have in your hand in your book also, or if you are having steam table separate book, there also you will have. You see, as I told you, this is the Mollier chart. You see in the y-axis I'm having enthalpy. Okay, it is a HS plot, right? The Mollier diagram is the HS plot. So you have to just recognize the lines. Okay, some of you you may be knowing this. Still, I'll take 2-3 minutes for this. Then we'll start the problem. So in y-axis we are having enthalpy your H. Okay, specific enthalpy. Always remember specific enthalpy. Kilojoules per kg. Okay, enthalpy. And in x-axis we are having specific entropy. They have not mentioned, but it should be written specific entropy. Kilojoules per your kg Kelvin. Now see this red line, this red one, this thick red line is the actually the Vapour dome basically. Okay, thick red line. Okay, thick red line. Okay, you can see the thick red line. Thick red line, my cursor, right?
Yes.
Okay, this is the
Yes,
nothing
sir.
but the Vapour dome, and this point is the critical point. Somewhere over here I'm having the critical point, and this is the trend of the HS plot. Not full HS plot is shown on the right side from the critical point is shown. Now this thin red lines, whatever you are observing, let me zoom. This thin red lines, whatever you are observing, you can see here 0.95 or zero point 0.9. These values you can see. What are these? Who can tell me? This thin red
The
lines.
dryness fraction.
Dryness
Dryness
fraction.
fraction. Very good. Dryness fraction. That means for different dryness fraction, I can get the values from 0.75, 0.8, 0.85. Now see, in some cases you are having say 0.875. Okay, so 0.875 means that point will be just in the middle. That is the approximation you have to take. Okay, somewhere over here at the middle it will be. Okay, so or 0.85, 86, 87 like this. You have to count over here in the gap, and you have to take the corresponding value. So this is the dryness fraction lines. Now see the constant pressure lines. Let us come to the constant pressure lines. You see here the maximum on 500 bar, it is written at the top. That means which lines? These blue lines. Can you see these blue lines? Blue thin blue lines. Here it is written 200. In terms of bar it is given. Okay, you have to convert into pascals and all while you will solve the problem. If it is in the bar, that is fine, but always keep in your mind the unit. This blue lines, this 200 is written, 100 it is written, 50 it is written. 50 means this one. 50 written means not the upper one, below one. Okay, so this line is the constant pressure line, and that is coming through, that is coming throughout from this portion. And that pressure you see gradually it is reducing. Where it is going? 0.5 bar, all the unit is bar, 0.2 bar, and you see it is coming up to 0.01 bar, right? So below this pressure 0.01 bar, you cannot measure anything. Up to this clear? The pressure lines, these blue lines are the pressure.
Yes, sir.
Okay, next is the constant temperature line. Constant temperature line means these green lines. I think you can see these green lines are starting from here and it is going like this, starting from here and it is going like this, and you can see the temperatures also. These are the constant temperature lines. 750 degrees Celsius, 700 degrees Celsius, 650 degrees Celsius, and like that. So in this way, you see it is gradually decreasing. And what is the minimum? You can see the 50 degrees Celsius over here, right? And below which it is not mentioned, but I can see okay, below 50 degrees Celsius I cannot see any temperature lines. So below 50 degrees Celsius there is no value. So from 50 degrees Celsius up to 750 degrees Celsius you can measure the temperature, constant temperature lines you can track, right? For a particular temperature and pressure, say I have to find out one point, that is, this is very important. Say I am telling that my pressure is say your 5 say it is my 4 bar, 4 bar pressure, the boiler pressure. Say I, for example, I'm giving you 4 bar, and it is my say your 700 degrees Celsius, 4 bar, or say I'm saying your 550 degrees Celsius. 4 bar means which line? I'm locating the point. You see this line. This line is the 4 bar, isn't it? Please response.
Yes,
This
sir. Yes,
line,
sir.
this line is the 4 bar,
Yes, sir.
and
Yes, sir.
550 degrees Celsius means this one is the 550 degrees
This
Celsius.
one.
You have to take the intersection point. This point. That is the required point I need. Okay. Say that is the condition it is given inlet to the turbine. Inlet to the turbine condition is given some amount of pressure. Say for example 4 bar and your 550 degrees Celsius. That means 4 bar 550 degrees Celsius means just you have to use the Mollier diagram, track the 4 bar line, track the 550 degrees Celsius this line. The intersection point will give you that required point. Okay, and this is the say the turbine entrance point, and obviously the line will be vertically dropped, and gradually where in the condenser pressure say it is sent 0.02 your bar, no temperature is required. Why no temperature is required? You see, once you have fixed this point 1 over here 550 degrees Celsius 4 bar, use your scale and drop down a vertical line, perfect vertical line, up to which line? 0.02 bar. 0.02 means just my cursor hand is over here, this line you see here it is written 0.02. That means the vertical line while it is intersects this 0.02 line, that is the entry point to the condenser. Is this point clear? Or the turbine exhaust, whatever you say, the turbine
Sir, it
exhaust.
is the entry point to the condenser or
Yes,
turbine exhaust.
entry point of, yes, turbine exhaust and condenser entry is the same point, right? So
Sir,
how I will
pressure
get?
will be reduced this much, sir.
No,
0.02.
I'm giving only example, but obviously
Acha,
the pressure,
okay, sir.
obviously
Okay,
the
sir.
pressure will be less, because in condenser the vacuum is maintained. It will be
Yes, sir. Yes,
obviously
sir.
below 1 atmospheric pressure, right? But
Yes,
I'm
sir.
giving you one example how to locate that point. How to
Okay,
locate
sir.
that point? If you know the condenser pressure only, from the point 1 that you have tracked, just use your scale and drop down a line up to that corresponding pressure, and stop where it is just you're intersecting that pressure line. That is
Okay,
your
sir.
condenser entry point, right? So in this way you have to find out. For the reheat also, there also the same concepts will be used. Corresponding pressure and temperature you have to see, and you have to find out, okay, the corresponding point. Once you are finding out the point, say for example this point initially I have found out, what are the properties at this point? I can find out the h. That means from this point I'll go to the left, I'll place my scale, I'll go to the left, say for 550 degrees Celsius, this point, I'll go to the left, I'll get the value of enthalpy. Here the graduation is not given properly, but whatever the Mollier diagram you will be having in your book, there you will find the proper graduation over here, and you will get the value of enthalpy from the y-axis. You will get the value of entropy from the x-axis. Just use your scale. From that particular point, go to the left for getting the enthalpy, go downwards, drop down, just locate that particular point on the x-axis by using scale, get the value of entropy, specific entropy from this x-axis. So is it clear how to find out h values and s values for a particular point?
Yes, sir. Yes,
Okay,
sir. Yes, sir.
thank
Yes,
you.
sir.
So this
Yes,
is the
sir.
basic idea you should have. So that's why I have taken 5 minutes over here, because until and unless you don't know this one, because steam table you know how to find out for a particular pressure, temperature.
Ajay, sir, what is this red line signify? What does it signify?
Thick red line. Thick red line
Ah.
is your vapor dome. That means the saturated vapor line.
Okay,
Okay.
okay.
And
And
the
these
thin
thinner
one-
red lines?
thinner red lines are the for the dryness fractions.
Okay,
Constant
okay,
dryness fraction. You
okay,
see over here it is written 0.95, that is the dryness fraction. 0.9,
okay.
0.85, it is gradually reducing. That is
Reducing.
obvious. If we go left, the dryness fraction will reduce, right?
Yes,
So
yes, yes,
this
yes.
thin red lines are the constant dryness fraction lines. And
Okay.
here, as per your diagram, but whatever diagram you will be having, you have to just you locate. It may be dotted. In some books I have found, I have seen some dotted lines are using, they are using. Okay, so that particular identity, some identity will be there, either color or some different types of lines. Some identity will be there to segregate different types of lines. That means constant temperature line, constant pressure lines, and constant your dryness fraction lines. These two things, these three things you have to find out.
Okay.
Okay, so let us now see some problems. Time is there. I think two problems I should discuss at least. Okay, can you see this 12.3 problem in this PDF?
Yes, sir.
Yes, sir.
Okay, so read this problem. It is from your book. You can see also, or just whatever book you are having. If your concept is clear, you can find out all these enthalpies and all. You have to find out the enthalpies basically, so that you can calculate the efficiency and all other parameters. You read the problem. A cyclic steam power plant is to be designed for a steam temperature at the turbine inlet. You see, the turbine inlet condition is given. Only temperature is given, 360 degrees Celsius. Turbine inlet, which point? This one point. You see, the temperature is given, 360 degrees Celsius. Exhaust pressure of 0.08 bar. Exhaust pressure means which pressure?
Sir, inlet at the condenser.
Yes, that means the condenser pressure. Throughout the
Or
condenser, the pressure
turbine
is
exhaust pressure. Yes.
right. The turbine exhaust pressure or your condenser pressure. Exhaust pressure of the cycle means the obviously the condenser pressure. That is 0.08 bar. You are asking about 0.02 bar, right? It is my 0.08 bar now. It is high vacuum is maintained. Okay. After isentropic expansion in the steam turbine, the moisture content at the turbine exhaust is not to exceed 15%. That means what is the value of your dryness fraction?
So
85, 0.85.
85%. That means
Yes,
0.8.
0.85.
0.85. That is the, you can say, the quality of steam, or you can say the dryness fraction. That should be maintained, 0.85. Determine the greatest allowable steam pressure at the turbine inlet. Turbine inlet means which point? Point 1, right? That is the turbine inlet. And calculate the Rankine cycle efficiency for these steam conditions. Estimate also the mean temperature of heat addition. Okay. So how to, first you have to draw in each and every type of this problem, you have to draw the TS plot. And which parameters are given, you have to mention those first. This temperature is given, this pressure is given, okay, and this pressure is given, you see, and this 0.8 bar is also given. This condenser pressure is given, this dryness fraction value is given. Okay, so can you find out this 2s point in the Mollier diagram? Please think of 10 seconds in your mind. Can you find this? Can you locate this 2s point?
Yes, sir.
You know the pressure, you know the dryness
Yeah,
fraction.
pressure
yes,
and
sir.
temperature.
Yes, sir.
Pressure and
Right?
temperature.
Right, so
Yes,
you will
sir.
have one intersection point using these two data, and you can get the value of 2s. Once I am getting the value of 2s, what I should do? Any idea? Only using the Mollier diagram. I will come to the steam table later. Steam table by solution can be done by Mollier diagram or by the steam table. That is up to you. But let me first ask you about the steam table that just we have discussed. Once I am getting this point 2s,
enthalpy.
yes, enthalpy, very good. Enthalpy I will get from the Mollier diagram. This H2S value I will easily get, and S value also I will get. The entropy also value I will get. What else I can get? I can get anything about 0.1, because you see, from the 0.1 only temperature is given, pressure is not given, right? The temperature is only given, 360
Yes, sir. We
degrees
can get
Celsius
the
is given.
pressure at 0.1.
Now see how I can get from the point 2s. Once I have located, just use your pencil and locate that point on the Mollier diagram, this 2s point. Now use your scale, vertically draw a upward line on the upward side, okay, and whenever you are having 360 degrees Celsius constant temperature line, intersect, it will intersect, that vertical line will intersect that constant temperature line, isn't it, at some point?
Yes, sir.
Look at that point. I'm repeating this step. From this point 2s, whatever you are having 2s, because you are having the pressure, you are having the dryness fraction, you can look at this point 2s. Use your scale from this point 2s, go upwards. Now you will have constant temperature lines like this over there, 350 degrees Celsius and 360 degrees Celsius, say some line you have found out. And this vertical line will intersect that 360 degrees Celsius constant temperature line. Stop that. Stop at that point. And that point is nothing but 0.1. Now, after locating that 0.1, you have to check which pressure line is passing through that 0.1. because pressure line is also passing through. Constant pressure lines are also passing through that region. So which pressure line is passing exactly, or minute change may be there, exactly try to find out exact pressure line, which pressure line is exactly passing through that particular point you have located. You will get the boiler pressure or not? Tell me, you will get the boiler pressure or not?
Yes,
Yes,
sir.
sir.
Okay, so that is the trick. Without without calculating a single, without calculating a single value, you can easily track the boiler pressure that is needed. You see, it is the needed steam pressure at the turbine inlet, that is the steam pressure at the turbine inlet, or the boiler pressure you should say. Okay, so just using Mollier diagram, if you know how to find out, if you know how to locate the points at different pressure, temperature and all, you can, without calculating, you can say the value, right? So that is one trick. But let me see how they have calculated. S to S, okay, you see they have used steam table. They have used steam table, that is very clear. In the first step, you, the well known equation S to S, that means at this point, to S point, what is there? Pressure is given. So at that particular pressure, this is a saturation pressure, right? So go for the steam table. So the first method that I told, that is a separate method, and this method whatever they have calculated, that is a separate method. That is your choice on which method you will go. Now this S to S, you see, uh, your SF means this point is the SF, and this SFG you can get, this SF and SFG will get from the steam table. How you will get? At this 0.08 bar pressure, at this 0.08 bar pressure, if you find out the saturated pressure table in the steam table, you will find out this SF and SFG value. X to S values is, this value is given in the problem, so you can easily calculate at the value of this value of S to S. Now this S to S value, you see, you will get easily from the Mollier diagram also. So that is up to you. Now S1 is equals to S to S, that is very obvious. I will consider as a ideal Rankine cycle. Okay, so S1 should be equals to S to S value. So S1 is this one. Okay, now what they have written as state 1, the temperature and entropy is known. Temperature is known to you, that is given in the problem. Now at this temperature, now this at this temperature, Sg value they have calculated, they have got this value from the steam table. Okay, now this 360 degrees Celsius, at this 360 degrees Celsius, the value of Sg obviously you will get from the steam table, saturated value, saturated steam table. Two types of steam table is there, saturated and superheated, right? So in the saturated value, from the saturated table you will get the value of this Sg, which is less than S1. Now it has been found the Sg value, you can get this value from the steam table, which is less than this S1. So from the table for the superheated steam, at the T1 this and S1 this, the pressure is found to be 6.823 bar by interpolation. Now see, here this part is very difficult in the sense you can go for it, you have to use interpolation. That means you know the mathematics, you have used the interpolation, that same interpolation, two boundary values you are having, and in between any value, if you want to calculate, the method that we follow by mathematics, that is your interpolation. So which two values you are having? You see, from the superheated steam, as it is clear now, it is in the superheated zone, the T1 value is given and S1 value is also given. S1 value we have calculated, so the pressure is found by the interpolation. Now this part they have not shown how they have calculated. Now my opinion will be, if you can check, you check today, you are getting this value by calculation, by interpolation you can get this value, but using Mollier diagram, are you getting this value or not? It may be minor difference after point, but 16 point something if you are getting, then you can go for the Mollier diagram, and you can save your time. That is my opinion. Or you can go for interpolation, that is your choice. Now the greatest allowable pressure is P1 is this one. Now once you are getting the P1, now P1 and T1 you know, T1 is 360 degrees Celsius, so you can calculate the value of H1. Now this H1 also you can calculate from the Mollier diagram also. H2S they have calculated using the formula, this like entropy, here just only this H2S equation will be what, H suffix F plus X2S into H suffix Fg. So using that value, now all these values you have to find out from the steam table, and you can calculate the H2S value. H3 value similarly you can get. Okay, H3 value you can get from the steam table, because it is a, this H3 value is what value? H3 value is nothing but the at 0.08 bar, it is the value of HF or not. Tell me. Is this clear? H3 value. You see here
Yes,
also
yes. It's HF.
173.88. Here also 173.88. Okay. Now, so this is the same thing. This point. That means it is your HF, saturated liquid. So H3 you are getting. Now all the parameters, all the H that you require for calculating the efficiency, all those parameters several times I have shown you in the slides. All those things you have to calculate for the corresponding Rankine cycle. Separately you have to calculate Q1. Once you are getting this value enthalpies, 4 enthalpies, you will easily calculate WT, WP and all those. I think they have done that. Yes, WT, H1 minus H2S, simple calculation. WP is also there. Okay, this WP is this one, H4S minus of H3. Now this I have discussed earlier how to calculate this pump work. Okay, in the first class. Okay, this pump work, first or second class. The pump work, you have to VDP basically. Basically, it is my VDP, right? Can you remember VDP, right? This VDP equation I have shown you in the pump work. Okay, why that is VDP, how it is coming, I have shown it, and you can find it from your book also. So that is the pump work, because in the problem nowhere it is written that neglect the pump work. So you have to take the pump work in your calculation. Now these minute things matter in the gate, right? These minute things matter in the gate. If you neglect this 1 point something, there will be some change in this efficiency. So once you are not having the exact value, you will think that you have done correctly, all the process is correct, but you will not get the marks. You may get marks in your semester, few marks, but you will not get the marks in your gate or something exam like that, like GATE. So these things, minute things, you have to keep in your mind. And once you are getting the efficiency, the mean temperature of heat addition, earlier also you can calculate that H1, that means Q1, that means the concept of your TM1 is what? H1 minus H4S, that is the Q1 is equals to TM1 into, that is the mean temperature of heat addition multiplied by S1 minus S4S. So that ratio. So all the values we are having. So we'll just put the values and we'll get the mean temperature of heat addition. This problem is very simple, but the starting of the problem is bit different because the pressure is not given. That pressure you have to find out, the boiler pressure. If you cannot find out the boiler pressure or the turbine inlet pressure, you cannot solve this problem, because until and unless you cannot find the boiler pressure, you cannot find out all the enthalpies. Okay, so is there any doubt about this problem? Tell me. This part, whatever you told, interpolation part, you can go for the interpolation part, or whatever I have shown you through the Mollier diagram, you can skip those difficulties over here. Okay, you can directly get the values. Okay, you can, I will suggest you to check by calculating, by taking the values from the Mollier diagram, calculate the problem and check it, that whether it is coming nearly or not. Okay, so is that clear, all of you?
Yes, sir.
Okay, so practice this type of problem. On the next class I will discuss more problems. Okay, some reheat problem and regenerative problem. Time is short today, and yes, I will try to share this meeting link today itself. I will try. Okay, because I have to the drive link, if I share, you have to download it, but if I share the YouTube link, you can see this, right? So I think I have to create the YouTube link.
So
Then
you can create a Google Classroom.
there I will share this drive link.
No, sir. Directly you can share the, I think, the
Okay, okay, let
YouTube
me
link.
see. Let me see. I'll share it. Okay, let me
Okay.
see. Okay, I'll share it either as your YouTube link or the Google Classroom if I can. Yes, that is better. I think that is a good idea, right? If you need these lectures, if you think that you listen to later also, then also you can listen, right? So
Yes.
I think that will be helpful for you. Okay, so okay, I'll keep that in your mind. In my mind, I will do that. Okay, let me see once which one is more feasible. Then I will do it. Okay. So I think you are having class also, next class, and all of you have given the attendance. All of you have
Yes,
given
sir.
the attendance, right, in the chat box.
Yes, sir. Yes, sir.
Okay, so thank you. Thank you for attending.
Thank you, sir.
Thank you, sir.
Okay, thank you. See you in the next class.
Thank you, sir.
Please practice more problems. Okay, so that it will be helpful for you for the next class also. Okay.
স্যার একটা প্রবলেম ছিল, পরে ফোন করবো স্যার।
হ্যাঁ, তুই আমাকে কল করবি, তুই আমাকে কালকের পরে
ঠিক আছে।
কল করবি, আই উইল বি ফ্রি।
ঠিক আছে,
ওকে,
ঠিক
আফটার
আছে,
টুমরো ইউ
ঠিক আছে।
কল এনি টাইম। ওকে, থ্যাংক ইউ অল।